Welcome back to the final segment of week 4. We are going to get into our last and one of my favorite applications of MaxFlow. And this is called the sport elimination problem. And I'm going to give you an example with team names borrowed from the IPL. So if you're watching a tournament and it's not clear that your favorite team is going to win and you're somewhere in the middle of the tournament, you must have certainly participated in discussions along the lines of, if Sri Lanka loses to Australia and then there is a washout in the match between New Zealand and England, and if this happens and that happens and then maybe India will have a chance to move into the semis or to the finals or whatever. So we are going to try and have those discussions today, but we are going to see if we can make them a little more exhaustive in terms of the case analysis and see if we can actually come up with an algorithm that will always determine if our favorite team has a chance or not, right? So let's try to formulate the problem statement with an example. So for instance, let's say that we have a situation where these 4 teams, Bangalore, Chennai, Delhi and Kolkata, have won a certain number of matches so far. And let's say that number is, or those numbers are 90, 92, 91 and 91. I realize that these may not be particularly realistic, but let's just say that there's been a lot of cricket going on and they've played all of these matches, and by now they're pretty exhausted, so there's only 5 matches that remain. And let's say that the matches that remain are essentially all the possible matches that you can play between 4 teams. I would amount to 6 matches, so let's say except for Chennai and Bangalore, right? All the other matches are supposed to still happen, right? All the other teams are going to play off each other. So the question we are asking ourselves at this point is, can these matches have an outcome that is so that the number of matches won by Bangalore at the end of the day is at least as much as the number of matches won by any other team, right? So in some sense, can Bangalore at least tie for the top spot in terms of total number of matches won? And let me actually draw this out like a diagram here. So these are the remaining matches and the scores are written next to the team names. Notice that the only team that's not playing each other is Bangalore versus Chennai. This would be a good place to pause the video and think about whether Bangalore stands a chance at all, or there is no way that, no matter how the remaining matches turn out, there's no way that Bangalore can even hope to tie the points table, tie on top of the points table. Right. Okay, so I hope you've had a chance to think about this. Basically, for now, we're going to play God for some time and we're going to say, okay, this is how the match outcomes are going to happen, because we want to do a thought experiment where we want to give our team, our favorite team, the best possible chance, right? So clearly we want Bangalore to win the matches against Delhi and Kolkata because we want to maximize Bangalore's chances of a final win. I know I've said in the past that we should be careful about doing things greedily, but it turns out that this in fact would be also the right thing to do. We don't help ourselves by having our favorite team lose matches in our thought experiment. So in our hypothetical scenario, we have Bangalore win against Delhi and Kolkata. This way, Bangalore's final score turns out to be 92, and what we want to do is prevent anybody else from reaching 92. But notice that, if we wanted Bangalore to strictly win, we already see that that's not possible because the maximum score that Bangalore can end with is 92, and Chennai already has a score of 92, and you have no negative points here. We are just counting the number of matches won, and even if there is a tie, it would basically count for either nothing or 1 to each team, and in any case you don't reduce the number of matches that you have already won. By the way, speaking of ties, let's just assume that there are no ties in these games, just for simplicity, although most of what we say can be easily extended to the setting when there are ties. So anyway, we see already that Bangalore has no hope of strictly winning or being on the top of the points table by a margin, but we come back to our original question of, can we at least hope to pull off a tie? And to that, we know that then if we want Bangalore to have a tie at the end of the day, then it must be the case that Chennai loses both the matches that it has remaining, because otherwise it's going to win over Bangalore, and that's not the outcome that we want. So let's say that we have Chennai lose both of its matches. So by the way, I'm implicitly following the convention here that if an arrow is pointing towards you, then that's a match that you have lost, right? So an easy way to remember that signage is that I think of the arrow as being a greater than symbol. So, so the way I read this off is that Kolkata dominated Chennai in this match that happened between them. But you can really pick any convention and stick to it as long as you're consistent and don't change your mind halfway. It's completely fine. All right, so we have this situation where we have locked in Bangalore and Chennai's final scores by predicting, or well, not necessarily predicting, but hoping for these match outcomes between the matches that they have remaining. But now we come to this sticky issue of what about Delhi and Kolkata. Notice that both of their scores have gone up by 1 each because they won this match against Chennai. Both of them have this situation of having 92 points now. And like I said earlier, we are going to say that there are no ties. So there's going to be one win in this match. It's going to be either Delhi or Kolkata. But from our point of view, it doesn't really matter because either way, we are going to have a team that strictly overtakes Bangalore's score, right? So we can conclude from all of this that no matter how things play out, our analysis here has been pretty exhaustive. So no matter how things play out, Bangalore has no chance of either strictly winning or even tying at the top of the points table. So, well, this is something that we figured out by sort of manual case analysis. And one of the questions we would like to ask is, well, can we figure this out in a more systematic way? So let's actually try to introduce some notation to capture the input to this problem. So we have a set of teams S, and for each team, we know how many matches they have won so far. And for each pair of teams, we know how many matches are remaining between them. And of course, crucially, we are given a concept of a favorite team, and we want to know if our favorite team can win, which is to say, is there a way in which all the remaining match outcomes can be set up so that if all the matches actually play out like that, then my favorite team is going to be on top of the points table. Now you can decide if you want to play for a tie or whether you want to play for a strict win. Either way, it's just going to be a minor adjustment in the way we actually end up formulating the problem. So it doesn't really matter which question you're asking. Both of them can be answered in pretty much the same way, the way that we're going to discuss now. So let's try to, first of all, make a little bit generic the nature of the argument that happened here, which basically said that, you know, our favorite team doesn't have a chance. So what was going on was basically the following situation. So you have a certain max score that you can hope for from your own team. And this maximum score is going to be, well, the sum of all the matches that are remaining for your team. So that's going to be, well, we introduce the notation WXY to denote the number of matches remaining between X and Y. So let's look at WXZ for all teams that are basically not X. And these are all the chances that your favorite team has for itself. And let's say that they actually go on to win all of these remaining matches. It's a little bit unrealistic, but it's our best case scenario. So let's pedal for it. So that's one component of the score. And of course, you also have the matches that they have already won. So that is WX. So this is really the maximum score that we can hope for our team to get in the best case, right? So I'm going to denote this value here by M, okay? And if some team already has won M matches, then there is no hope for your favorite team to strictly win the whole tournament, because as we have discussed earlier, this is not a value that can reduce as more matches are being played. And if some team has won M+1 or more matches, then there's no hope for your team at all. They will not even tie because somebody has already scored more than the best possible score that your team can achieve, right? So those are some simple special cases that you can get out of the way directly. But let's try and figure out what was also going on in our kind of situation here in this example. What was happening was that we had these three teams that between them had 3 matches left. And we said, okay, look, no matter how these matches go, somebody is going to basically overshoot the score of 92, which is our M here, right? And if you think about why this happened, of course, we did it through sort of a case analysis. But if you think about why this happened, you can probably conclude this on your own here, which is basically the following idea. Look at the total amount of score that has already been accumulated. That is 91 plus 91 plus 92. So that's a total number of 274 matches that have already been played. And there are 3 more matches that remain between these 3 teams. If I just focus my attention here, there are 3 more matches remaining. So at the end of the day, we know that it's a score of 277 that is going to get distributed among these 3 teams in some fashion. I don't know how these matches will play out eventually, but no matter how they play out, there's a score of 277 that's going to get distributed in some form or fashion between these 3 teams. And notice that our M value here was 92. We can't afford any team winning more than 92 matches. If that happens, then our friend here will not even be able to shoot for a tie at the top of the points table. But on the other hand, notice that 92 times 3 is 276, which means that it's not possible for all the 3 teams here to actually end up with a score of at most 92 each, because if that happens, then the total number of matches that are distributed between them basically falls short of the actual number of matches that they are going to play between them, or the actual amount of score that they can accumulate. So some of this older score is perhaps coming potentially from other matches, but hopefully you see the argument here, which is that, well, if everybody had to end up with a score of at most 92, then their total score will be at most 276. But because of this situation out here, we know that the total score, once all matches have been played, is going to add up to something that is more than 276. So this is an application, if you like, of the pigeonhole principle. More generally, what we are saying is, if there exists a subset of teams, so we used S to denote the set of teams. So let's say that there is a subset of teams such that if you look at all the matches that these teams have won, so that would be summation WY, plus if you look at all the matches that they have remaining between them, so we're going to say XY in S, WXY. These are all the matches that remain between the teams in T. Right? So that's this quantity in the second term. And the point is that if this entire sum exceeds M times the size of T, that is the number of teams at play, then again we know that our favorite team really has no hope. And the reason for that is, again, similar to what was happening in the example. So remember that for our favorite team to have a chance, it must be that when all matches have been played, then in particular for all the teams in T, apart from all the teams globally, but in particular all the teams in T must have a final score of at most M, right? But now if we sum these final scores here over X in T, then notice that we get that the sum should be at most M times the size of T, because there are size of T many terms in the left hand summation and each of them is at most M. But that contradicts the inequality that we have written above just here. So this would clearly be a problem. Therefore, we know that if there is such a subset of teams where the total mass of the remaining games between them plus the total scores that they have so far ends up being in excess of M times the size of that set of teams, where M is the maximum score that our favorite team can hope to get, well, in this situation, we know that we can say no. We can say that our team has absolutely no hope. But what are the scenarios where our team actually has some hope? To identify this, and indeed to also identify that this is the setting that we might be stuck with, we are actually going to construct, no points for guessing, a flow network that captures this problem. So although I'm going to start off by describing the flow network here, this is a good time to actually take a pause and think about how you would do it yourself. Notice that intuitively there are two sorts of things that we have to figure out. On the one hand, we have to figure out how each of the remaining matches will ultimately play out, how many of them will be won by one team versus how many by the other. But on the other hand, we also need to constrain that each individual team accumulates only a certain number of match points, right? So these are the two constraints that need to be reflected in the flow network. So with those hints in mind, please feel free to take off some time to try and construct the network yourself. And we are going to get started with it right about now. So we already know that our flow network is going to have two special vertices. So let me put those down first. And now let me also begin by saying that, okay, let's account for here the matches that remain. So we're going to have a vertex here for every pair of teams that are going to play each other off still, right? So if, for example, this could be Delhi versus Kolkata, and we know that they have one match left. In general, you could have any pair of teams that have a certain number of matches left and introduce a vertex for each such pair. Okay, and the flow that passes through these vertices and gets split further down, that split will basically tell us who wins how many of these remaining matches. Okay, so where is this flow going to go to next? Well, a natural thing to put in here is the individual teams, right? So I realize now that I write this that this sounds like an oxymoron, but what I mean is I want to look at the teams as opposed to pairs of teams. That's what we have done in the previous column, right? So just as a sort of a concrete example, you might say that this would have entries like this might be Delhi versus Bangalore. This might be Chennai versus Delhi, and so on. Of course, we tend to keep our favorite team, and if that happens to be Bangalore, then it's Bangalore. We tend to keep our favorite team out of all of this because the matches that they're involved in, their fate is predetermined. I mean, not in the real world, but as far as our thought experiment is concerned, we know that those matches have to be won because we want the most optimistic estimate for M, which was the maximum score that's achievable by our favorite team. So let me actually write that down. So we have all the remaining pairwise games encoded here in the first column, and let's say that you have a vertex here that represents a game between, say, Delhi and Kolkata. Then I want this vertex quite naturally to link to vertices that are representing these two teams. So if this is the vertex representing Delhi and this is the vertex representing Chennai, then those are the vertices to which this vertex here gets connected, right? And this is what I was alluding to earlier. If you have a certain amount of incoming flow into the DD CSK node, then you want that flow to be split across DD and CSK, and that split will actually give you a hint about how many matches go which way, right? So to talk about that a little bit more, let's actually finalize these edges as well. So we have edges going from S to all the pairwise teams, and we have edges coming from all the individual teams down to T, right? What do you think the capacity of all the edges going out of S should be? Well, that should be the number of remaining matches, right? So if you're going to the vertex XY, then here the capacity should be the number of matches that XY have remaining, right? And on the other hand, if you look at edges that are coming into T, all of these edges must have a capacity of M appropriately adjusted for the number of wins that these individual teams have already had. So for example, if we have a vertex here that denotes the team X, then the capacity corresponding to this edge would have to be M minus WX, right? Because that's the maximum number of matches we want to allow for them to win. Notice that if there is any team for which this capacity turns out to be negative, we don't even need to build this network. We know that it's already a lost cause as far as Z is concerned. And if the capacities are at least non-negative, then we have a valid flow network and we can try to take it from here. So the capacities of the intermediate edges we are going to leave at infinity. It doesn't really matter because the control is coming from what's going on basically elsewhere. And notice that if we do have a flow that saturates all the edges going out of S, then we have legitimately an answer to the question of what should happen with these matches. So for instance, let's say that we have a flow of, and let's say that this flow is saturating. So let's say we have a flow of 5 units coming into DDCSK. That means that they must have had 5 matches left. And now let's say this flow gets split as 3 and 2. That means that Delhi wins 3 of those matches and Chennai wins 2 of them. That's according to the flow network's suggestions. Again, please keep in mind that none of this is about actually forcing match outcomes in real life. This is really just a mathematical curiosity about the existence of a future where our favorite team wins, and that's all that's happening. The suggestion here is not that, well, you take the output of the flow network and you try to actually make these things happen. Okay, so with that out of the way, let's see that once you have all of these matches determined in this fashion, if it's a valid flow, then all of this flow that's incoming to any vertex must be pushed out to T, and those capacities were adjusted in such a way that, well, we ensured that no team is winning too many matches relative to our favorite team, right? So if you actually have a feasible flow that respects all the capacity constraints across the board from left to right, then you actually have a way of orchestrating, and again, not that that's what we're going to do, but you have a way of assigning outcomes to all the matches that remain so that your favorite team actually goes on to win. What if the max flow turns out to be less than the total capacities of the edges incident on S? This would simply mean that you can't make it all happen. So there will be some matches that are basically indeterminate, or we are falling short. We will not be able to orchestrate everything in such a way that your team is guaranteed to win. And the lovely thing about this is that you basically look at where your max flow algorithm gets stuck, and notice that what you get is a ST cut, right? So you have S and you have a bunch of team pairs, and then you have some individual teams as well, and all of this is on the S side. And you look at the flow that's going out here. It turns out that you can actually imagine this as being evidence for the fact that your team cannot win. So it turns out that if you look at this cut and focus on the teams that landed up here, then those teams will actually be a witness for the pigeonhole style argument that we made a while ago to convince ourselves that our favorite team indeed has no win. So not only does the max flow network, when it works, when it gives you a sufficiently large flow, tell you how to organize the match outcomes in such a way that your team survives and either strictly wins or ties. By the way, the difference between strictly winning and ending up with a tie on the top can be easily encoded into these capacities out here. So that's something that you can easily adjust for. So whenever the max flow actually gives you sufficient flow to actually assign outcomes to all remaining upcoming matches, we are good. But when it fails to do that, it turns out that if you look at the ST cut, you can actually get a witness for why your team actually can't make it. So if you want to explain to your friend who doesn't know anything about max flows but is still very curious about why you're so pessimistic about your favorite team's future, you can actually give them the simple averaging argument by pulling it out of the min cut of a max flow and saying that, well, look, this is why there's absolutely no hope. So that's a bit of a calculation that I'm going to leave as an interesting exercise. There are some spoilers in the notes, so if you don't have a chance to verify it but you want to look it up, that's something that you can also do. All right, so with that, we come to the conclusion of all our discussions around the maximum flow problem. As I said, it's a really cool problem for at least two reasons. One, that it's been at the heart of a lot of algorithms research on its own right. It's led to the discovery of a lot of interesting techniques across the board, and research on faster max flow algorithms is an active subject to this day, even as we speak. And the other reason is that it turns out to be a really powerful paradigm or tool for solving other problems that may or may not immediately look like having any connections with flows or networks. But if you're clever about your reductions, you can really exploit and leverage the algorithms that we already know for max flow to solve a bunch of other problems. So there will be more pointers and more examples of that sort in the other materials across this course. So I hope you enjoy solving your problems this week, and I hope you had fun learning about flows. Next week, we are going to be talking about reductions still, but of another kind. These reductions were nice because they allowed us to create algorithms for problems that we didn't know how to solve otherwise. Next week, we are going to be talking about reductions that are used in the other way to justify why we don't or perhaps even can't come up with algorithms for certain kinds of problems. So as you may have guessed, we'll be talking about NP completeness next, and that's what's coming up. I look forward to seeing you there, and that'll be all for this week.